Hi, in this video we're going to be talking about area with parametric equations. So if we have a function parameterized by t, so say x is equal to f of t and y is equal to g of t, we want to find the area under the curve that's mapped out by these two values. So we're going to make an assumption, and we're going to assume that the curve is traced out only once from t equals alpha to t equals beta. So we wouldn't want a situation like if we were parameterizing x and y by cosine of x or cosine of t and sine of t. We would just want to consider 0 to 2 pi, for instance, because if we went from 0 to 4 pi, it would circle around twice and we would have double the area. So now let's find the area under the curve. Well, we know that in terms of x and y, the area is the integral from x equals a to x equals b of f of x dx. But x is equal to f of t. So that tells us that dx is equal to f prime of t dt. And now we can replace x and dx with our new values just in terms of t. So replacing that, and now we're going, instead of x bounds, we have t bounds. So when we replace this, we get the area is equal to the integral from alpha to beta of f of little f of t times f prime of t dt. But now we have a new problem. We don't know what big F of little f of t is. However, we do know that this is actually y. And we know that y is g of t. So let's go ahead and replace big F of little f of t with g of t. And when we do that, we get the area is equal to the integral from alpha to beta of g of t f prime of t dt. For this video's example, we're going to look at the curve described by the parameterization of theta instead of t, and x is going to be equal to 6 times theta minus sine theta, and y is going to be equal to 6 times the quantity of 1 minus cosine theta, as theta ranges from 0 to 2 pi. Now, before we get into what's the area below the curve, what does this curve even look like? And to describe what this curve looks like, what we're going to do is we're going to start with a circle. We can think of this as like a disc or a hula hoop on the ground. And we're going to mark the bottom point on this circle, and we're going to rotate this circle along the ground without slipping, and then trace the motion of that point as the circle rotates from 0 to 2 pi. And this motion, which is kind of described above, actually marks out what is called a cycloid. And the steps to create this cycloid are written on the screen before you. So now that we know what this graph looks like, let's actually find the area underneath the curve of it. So we're just going to rewrite what x and y are in terms of theta and our bounds for theta. So area, again, remember, is the integral from alpha to beta of g of t f prime of t dt as our general formula. So in our case, alpha is going to be 0, beta is going to be 2 pi. G of t is actually equal to y of theta. So that's going to be 6 times the quantity of 1 minus cosine theta. And f prime of t is going to be dx d theta, which is going to be 6 times the quantity of 1 minus cosine theta. And that's also going to be times d theta, right? Because we have f prime of t dt. So our area is going to be equal to the integral from 0 to 2 pi of 36 times 1 minus cosine squared theta, or cosine of theta squared, d theta. And now what we're going to do is we're just going to integrate this. So we expand out the square, and we get the area is equal to 36, because we can pull it out, it's a constant, times the integral from 0 to 2 pi of cosine squared minus 2 cosine plus 1 d theta. And this is simple integration. We know how to do this, so I'm just going to speed up through it. If you need to slow down the video or pause at a certain point to figure out one step to the other, please feel free to do so. Now we could plug everything in at this point, and we would have to do a lot of writing and a lot of work. But when theta is 0, everything is 0. So we can just ignore the 0 part. And then when theta is 2 pi, the signs vanish. So what we end up getting is 36 times 3 halves times 2 pi, which ends up being 108 pi. So I'll leave the rest of the steps of the integration here. And if you have any questions, comments, concerns, please leave them in the comments below. And as always, thank you for watching.